as it was mentioned, I got my bachelor's degree in mechanical engineering at Hopkins. I also got a master's degree in robotics. I currently work as official job title an avionics engineer at Blue, but I work on the BE-3U engine, which is the upper stage engine to the New Glenn vehicle that Orlin was talking about. So that's our orbital vehicle. Second stage means that separates and goes to orbit afterwards. And I do controls and simulation. I concentrated on controls and systems in my grad degree, and so spoiler alert, that's what today's presentation is going to be about, a little inside look into the world of controls. And I also titled this a balancing act, and stay tuned, you'll find out why. So controls, or GNC, guidance, navigation, and control as sort of the more broad bucket term for this field, is really like the underlying science behind what makes autonomous systems autonomous. So here I have three different systems. We have a robot trying to fold laundry, a car trying to park itself, and we have New Shepard, of course, returning from space and successfully landing on the launch pad. So all these systems seem a little bit different. You may be thinking, okay, yeah, autonomous systems, the robot comes to mind, I'm scared it's gonna take over the world or something like that, or even the self-driving car, but you might not think that there's a lot in common between New Shepard, let's say, and like the car or the robot. But GNC is sort of what unites all these different systems. So what is GNC exactly? Guidance, navigation, and control is a design process, and the goal of this process is two things. One is you get your system, so whether it's your robot, it's your car, it's a rocket, in some desired state. And when I say state, that refers to any sort of parameter, physical parameter of your system that you can control. So if you're a rocket, it might be an orientation, or a satellite might be an orientation. If you're a robot, it could be like a manipulator position, like where is my hand? Is it actually picking up this laundry that I'm trying to fold? And then the second goal of the GNC process is to keep the system stable. And so stability is really just, is my system doing what I want it to? Is my engine actually turning on and going on to the power level that it is? Or is it in some unstable state that I don't really understand what's happening, and then that could get dangerous because, you know, you might have an explosion or something like that. And then the process seeks to specifically answer these three questions, and it does so in an iterative way. So you're constantly undergoing these three steps. So one, your guidance phase will be answering the question, where do I need to go? Your navigation phase is the state determination, so where am I now relative to where I need to go? And then control is actually the command execution, so manipulating your system to actually get it to that point. So if I were to rename this initialism, I would actually call it NGC, because before you really do anything, you need to figure out like where you are in the world. So navigation is a whole field of utilizing sensors and predictions to be able to track movement and determine this current state of the system. So there's a lot of science behind different types of sensors. We have gyroscopes, which are orientation sensors, so a lot of times satellites will use those. We have radar, lidar, sonar, which are more position sensors. So I'll play this again. I got to play with cool robots in grad school. This is us driving one around on just our quad, and it has a lidar cone on the front. And this down here, you can see it's actually assembling a map as it goes along of where different obstacles are around it. And the more that you drive it, the smarter it becomes, the more it's able to understand where those different obstacles are. I think everyone's familiar with GPS as some kind of navigation tool, maybe is really reliant on it like I am. And then common filters are more of that prediction aspect of navigation. So maybe you have a measurement and you have an understanding of what your system is doing, and a common filter will try to reconcile differences that may arise and give you the most accurate measurement possible. And accuracy is really critical in the navigation step, because you wouldn't want to be controlling something that you don't really know if it's actually there or not. The next step is guidance. So this is really physically driven, really math driven at times, trying to understand the way your system actually transitions between different states. So how does this robot move all of its joints? How does the marker get from one point to the next? If I'm a rocket, what aerodynamics are going on that as I ascend in my flight, what sort of effects does that have on my rocket? And then using this very physical understanding to actually calculate how you will get what sort of forces or inputs you need to apply to get to your desired point. So there's a few different techniques that you could use. Differential flatness is something where you can parameterize your system. So if you have a few different states, maybe you can express them all in terms of one, because it's way easier to control one thing than it is to control 4 or 5. You can use optimizations. So if you're a self-driving car and you have some algorithm that tells you you need to go straight and that's where your parking spot is. But it might also tell you, or you can turn around in a big circle and then get to your parking spot, but one obviously is less annoying and takes less time. So that's optimization is a key part also of a lot of guidance algorithms. And then some more advanced modern systems might even utilize artificial intelligence. You know, maybe I just need to drive my car in a straight line to get to where I'm trying to park it, but what happens if a person walks in front of my car or something pops up that I didn't know about before, and how will my system recognize that and react? And then I also put kinematics on here because it's one of the simplest but also most robust guidance systems. So I'm sure everyone can think back to like high school physics and just basic kinematic equations. If you're at some position and you're moving at some speed over some amount of time, you're going to get to a new position. So boom, you just did guidance. And that's really what's going on here actually in this robot that we're playing tic-tac-toe with. We have a understanding of the lengths between the different joints, the forces that are acting at the joints, and that's how we're able to really express what is the relationship between the base where I'm commanding the robot and where this marker position is. So the result of your guidance step will be a set point. So that's saying you need to go here. You either need to go to just your next step or you're close enough that you can go to your final step. And that set point is the input to the last step, which is control. So control, or the set point, can be seen on this graph as go to height of 1. And the control step uses dynamics and inherent natural forces in your system to actually just finally adjust your current state to this new state. Has anyone taken a control class? I don't know what here. Okay, cool. So maybe you remember talks about frequency analysis or Bode plots and time domain and everything. Really what control engineers care about is how responsive your systems are, and that's what all that fancy math is trying to capture. So if you have a system that moves really quickly, you're going to get to the point where you want to be at faster, but you might risk actually overshooting it, as you can see on this graph here. This way overshot it, but it was moving the quickest out of the 3 of these systems here. Alternatively, if you move really slowly, you know you're not going to overshoot where you're trying to be at. You know you're going to stay stable the whole time as well, but you might just take forever to actually get to where you need to be. And so this whole concept of responsiveness and this trade-off between stability and performance is really manifested in what a PID controller does. It's one of the most simplest, most robust forms of a controller, and that just sort of scales, where am I right now? Maybe if I'm further away from where I want to be, I can move a little bit faster. Maybe if I'm closer to where I want to be, I can slow down a little bit and do that trade-off. Model-based predictive control is also common, especially in robotics, because you can get large data sets really, and then you can look at the data and say, okay, I know exactly how my system's behaving, I know exactly what sorts of forces or inputs this system needs in order to get to different types of states, and almost just explicitly use that as a way of control. And then finally, the difference between nonlinear versus linear systems, that just refers to, so going back to our car example, there's a pretty direct relationship between how I can move forward and what speed and what amount of time will get me to another position. But some systems might have things you either just don't really understand or can't directly measure, and how does that affect your GNC process? So how all this relates to autonomy is the ability to act independently. And a lot of high-performing systems like rockets or engines or even robots, it's really beneficial to be able to do GNC autonomously. If you are working as a manufacturing engineer for robots, you're dealing with really, really large systems that have a lot of force. It could potentially actually be dangerous for humans to go and directly operate. And so being able to use GNC and use this program to be able to get these robots to act autonomously on their own is really critical. Humans have always been capable of doing GNC. Like, if you just are driving to the grocery store, you're planning out where you need to go, you're making adjustments to your steering wheel, to your speed pedal as you go, and you're doing this over a long enough period of time that you can afford to actually just like make these corrections and make these decisions yourself. If you're a BE4 engine and you're shooting out 500,000 tons of force at once, as much as I'm probably sure there are engineers here who are like, oh yeah, I can do that, I can make those calculations, no problem, or whatever. The timescales that these systems are responding to are just so quick and they're so powerful that you get a lot back by just having computers do it, basically, and the processing power that comes with them being able to make quick decisions and quick calculations. Additionally, autonomy can give you benefits for like failure detection. What happens if something goes wrong? Your processor would probably be able to pick up on it a lot more quicker and start responding to it as well. So since this is a rocket-themed presentation, I figured I'd close things out with like an example. So GNC and rockets, and here I have a broomstick, which is not a rocket, but if you follow the analogy through, this broomstick, it's long, it's slender, it's super hard to stand up on its own, but it naturally wants to fall over as well or rotate. It has maybe more mass at the top of it. And you can use your finger to counteract the rotation, and really what your finger is doing is it's applying force in some direction. And maybe if it's tilting over a lot, you apply a bigger force to try to recorrect it, and maybe if you're doing a pretty good job, you're just making small little corrections. So rockets really use this same analogy to do their own sort of orientation control through an effect called engine gimbaling. And so engine gimbaling is what you can see here. If you notice, the plume of the rocket is moving back and forth slightly. That's it redirecting all of that force coming out of the end of the engine in some direction. And this, if it were attached to a rocket, would be able to actually control that rotation and that movement. So then in terms of like tying this all together, again, if anyone's taking a control class, this maybe looks like pretty familiar from like a textbook. But your guidance phase and how this all like relates to GNC, your guidance phase will give you some set point to the controller. So I'm New Glenn, I'm on my mission to hit some orbit, and I know that I need to be at some certain angle in order to inject myself into this orbit. So the guidance system tells me, hey, rocket, go to that angle. The controller says, okay, if I want to be at that angle, I know that my rebalancing, my broomstick, needs to re-rotate this much, and I need to apply this much force from my engine gimbaling in order to correct it, or in order to get it back into that position. So the controller is taking that set point from the guidance and translating it into actual real forces, real commands that are getting sent to the gimbal, to the actuators, and then in your system, you're also modeling how that has a full body effect on the actual rocket itself, like what are the aerodynamics that are going on, how did your system respond to this change that you made. And then understanding what the effect is after the fact, after you've applied this input, and getting that feedback now in your navigation phase as well, seeing the measurements from the sensors, the gyroscopes, your IMUs, to see what your orientation is. Has it successfully reached this attitude that you're trying to control it to? Do I need to make more adjustments? And that's where like the feedback loop comes in, and so you go on and on and on forever, trying to complete this loop. So that's really all that I have. I hope you all learned something cool about GNC and rockets. And yeah, if anyone has